for 9.3 about means and looking at when you are given a list of information, and this is very common to happen in the AP test because they don't want you wasting a lot of time finding these pieces that you need to be able to check things like your conditions. So let's check our conditions for this, comparing the mean weight of pineapples harvested this year to last year. First of all, are these randomly collected samples? And let's see, they did go out to the field and they went out and they took a random sample of 50 pineapples. So that was given. It's going to describe the pineapples grown out in these fields. Something that might not have been random would have been, let's say they had a special farm, the jumbo pineapple farm. I don't know. They have mutant pineapples growing there, like the Jurassic Park of pineapples. That might have given us something that was not random, but this is random. Okay, and so then now we need to know if this was independent, and we know that N is 50. So, and you actually can see it right here too, although it does have a capital N there, but they really do mean little n. Okay, so is 50 less than or equal to 10% N? And these are large pineapple growing farms. And so since more than 500 pineapples, we can say that that's, pineapples. And then is this nearly normal? Let's check that. And we see that since N is 50, is N greater than or equal to 30? Since 50 is greater than or equal to 30, CLT is met. So for means, you're checking CLT. For proportions, you're checking N times P, N times Q. So CLT was met. So even though CLT was met, you still kind of need to know, were there outliers? Because if there were outliers, you would need to run this test twice if you could. So I'm going to check for outliers, and how do we do that? 1.5 IQR. So let's do that. Let's check the max typical will be Q3 plus 1.5 times IQR. So let's see, the IQR is going to be this Q1, the Q3. So IQR is Q3 minus Q1. And so that, when we do the subtraction of those two numbers that you see right there, we end up with 4.125. So my max typical will be 34.115 plus 1.5 times 4.125, and that is 40.2985. Look at the max. That is within that value. Now let's check the min. And so the minimum is going to use the Q1 and subtract the 1.5 times the IQR. And so that will be the 99 minus 1.5 times 4.125. And that is 23.8025. So if you think of those typical values of being that 23.8025, and you've got up here, you've got your 40.2985, we see that the 35 is in there. That's that max. And we also see that the min, which was 26.491, is somewhere in here too. So that is no outliers. So that's good, because then that means that our conditions are met. And then, so what are we going to do? We have pineapple weights that we're looking at. It's one sample, t-test for means. Okay, next page. So let's see, now we've got the same output again, and we're going to do the t-test for means. So you'll want to define what you're measuring here, and our mean is going to be the mean weight of a pineapple in ounces. And we think that based on past practice, we saw pineapples usually were 31 ounces. But our data gives us a sample mean of 31.935. Our data gives us a standard deviation of 2.394. You can see that standard deviation right here. But they actually already found the standard error of the mean, which is what we're going to need for our analysis, the standard error of the mean, which is, of course, that standard deviation over square root of n. And so if you were to punch this into the calculator, you would get 0.339 and more decimals as well. But this will be, because they're giving us output, this is going to be adequate enough for our purposes. And they're pretty generous with rounding errors in general. But I'm going to put that in, find the shape here. Oh, well, let's write our hypotheses. Null hypothesis that our pineapples are the same as in the past, and our alternative hypothesis is that they are different. So different from the past. They didn't say that they wanted them to be bigger or smaller. They just wanted to know if they were different. And so that means that we're going to be looking at the mean being 31, but we're going to be looking at the two-tailed situation. So we will need to double our tail at the end of this process. And we have a t-value for this situation with our sample value minus our population value over the standard error that they gave us in their output. And that gives us 2.758. So what's the probability of a t being greater than a, because that's this number right, that t-value corresponds to that number right there. The t-value being greater than that, so make sure you go to the correct side. And for this, we're going to need to know the degrees of freedom. And it's 50 minus 1. Some textbooks would actually have us use a z, and we could use the normal CDF, but in APStats, they want you to use a t with unknown standard deviation, with sample standard deviations. And we're also going to have to think about what alpha level we're going to use. So I'll write that down. Okay, so we get 0.004074. And remember, that was using TCDF. Left, right being some huge number, like 10 even is huge. Now we got to double it. Okay, because it's two-tailed, make sure you double. All right, now that's our final p-value that will then write our conclusion. Since the p-value of 0.00815 is less than alpha equal 0.05. We reject the null hypothesis. And there is significant evidence that our new pineapples for this year, our pineapples are different from the past 31 ounces. So that they have changed, basically. They're wondering if they changed. We can tell them that the significance test is telling them that they changed. And that's doing a two-tailed test, which then that relates really well to the confidence interval. And here's some mini tab output that you might see something like this in a AP test, even on one of my AP tests. And you can see that there's the t-value that we actually just got on the other page. And here's the p-value that they're going to report in Minitab. And Minitab will always report a two-tailed p-value. So if you need a one-tailed p-value and you have Minitab output, you're going to need to cut that in half. So if one tail divide by 2, okay, so there's that. And so you can see the same p-value that we just got, a lot of the same information that we had on the other page. But this is also reporting the 95% confidence interval. So they are saying that they think, based on their sample, and that would have used, again, the sample standard error of the mean, it would have used that. And so it's going to really match up well, because you can see that 31 is not in this confidence interval. And so the confidence intervals and the tests are going to draw the same conclusion. Okay, and so I'm going to write that down at the bottom. I'm going to write my conclusion based on the confidence interval, because 31 ounces is not in the confidence. Remember, the confidence interval is made just from sample information, but I got to give the numbers of 31.255 to 32.616 ounces. It is not, or it is reasonable to conclude that there is a change in pineapple weights. Okay, and so on to the next page. So the connection between two-sided tests and confidence intervals is even stronger for means, and that's because means actually use the sample standard error in the t-test, unlike with proportions where you're using the no hat for the test and you're using the hat for the interval. So like there's a slightly different standard deviation used there, just very slightly different. But with the means, you're using the exact same variation. So That's why it's so highly connected. And two-sided tests are generally what we're doing unless you are very specifically wanting something to be higher or lower. To remind you how to get the to check these things, if I could just remind myself, going over to stat tests, and that was a t-test. We could have done the t-test for the pineapples in here. We would have gotten the same results. And then for the interval, I would go down to a t-interval would be the interval that I would have done if I wanted to check these using the calculator.